All right. Good morning. So let's continue on with our binary search tree. So we've done all the traversal code, and we actually talked about how we can insert into a binary search tree last time where we left off. And we talked about like 4 cases that need to be considered. Inserting when a tree is empty, or when the leaf has no children. Basically, a node that um, has no children is already called a leaf, so I should have just said leaf node. And also whether or not the node that you're at has only one child, or in all other cases, we just keep going down until cases 1, 2, and 3 are encountered. Now, when we first learned binary search trees, yeah, this insertion algorithm might not make so much sense, but it's not until like you start coding it and tracing like the process, it starts to make sense. And I'm going to try my very best to really do that, to just code it and then eventually get to the point where we can go deeper and understand the insertion process, highlighting every one of the cases. And then we can also um, check to see if our insertion algorithm works by using one of the traversals that we know. Keep in mind that in-order traversal results in an ordered traversal of every node. So meaning that if we were to print out every node as we move along through the tree in an in-order fashion, the order of which these nodes print out should be in sorted order. So that's good. So that's how we can know whether or not our in-order traversal is working correctly. Now let's actually start to code all this. Going back to our code here, let's actually write the code right before main. And the signature of our insertion is going to be something like void insert node. And then we're going to say, actually not insert node, let's just do insert. And we're going to take in our current root and also the value that we want to insert. So that makes it easier. So all the caller has to be responsible for in this case is just to maintain this root, because that is going to be the entry point to our tree. So if we imagine a tree like so, so let's say in this case we have a tree here. Oh my goodness, oh my goodness. All right, let's do that again. I'm hitting buttons again. So we imagine a tree. Okay. It's not built for lefties. The responsibility for us is to always maintain this. This node here is the root. So as long as we actually have access to this node, we can pretty much touch every single node in this tree through traversal. This is similar to a linked list where we had a chain of nodes. Given some head, right, head, we can access every single node in the list. So same thing here. This, instead of head, it's a root. Okay. We can also think about it recursively too. Like remember I said that in a linked list, as long as you have some access to some node, and you could pretty much consider that as like a head too. It's just that you'll start from here instead if your head is here, or you'll start from here if your head is here. So we had our root to be right here. We passed in root to be this node. Then you'd only have access to these 2 or these 3 nodes here, but you cannot touch any of these here. So it's based off of your perspective. Most of the time, your root is going to be at the very top of the tree, visually. Okay? My hair is all messed up. Okay. So this root here, we can imagine it as this point here where we can start moving down. All right. So the first thing we want to do is create a new node. And I think we can actually have a helper to create a node for that. So, to help us create a node based off of some value. So we'll have a new function that returns a pointer to a node. And remember, a node is actually just a node here is just our struct here. Okay, we're just gonna create a pointer to it. So I'll say create node given some value. Now, what we want to do is we are going to first malloc pointer to a node struct, and we'll call that result. So we can say we can cast that with malloc to size of node, which is that struct. Now we don't have malloc recognized, so that means we need to include stdlib.h. Then we should see it right there. So size of node will basically allocate some memory in the size of whatever this struct is. So in this case it'll be 488 because these are just memory addresses. So that's about like 20 bytes or so. And then we can just assign the value to be value. So this one passed in here. And then we can say result left is null, result right is null, and then we'll just return that pointer. So there we go, we created a node. So going back to insert here, we can say something like node to insert will be, in this case, what we got? Create node value. Okay? So now we have a node. Now, one of the cases when we insert is whether or not the tree is empty. We can tell the tree is empty if the root is null. It means that there's no tree, there's no entry point. It means this, if you can imagine a null tree, it's just basically an arrow pointing to void. Or we'll just call this null. What we want to do is then turn it into something like this. Okay, and this will be our arbitrary node that we create. So what we want to do is if root is null, we can just say, well, root now points to, in this case, node to insert. Now, does this actually work? Does it work? I'd say it doesn't. So let's go back to our exercise where we drew out our memory map with pointers. So what we're saying here now is that we want to assign the pointer node to insert, which is a memory address, to be the address that root points to. But keep in mind that this in C, function calls are always copied by value. So actually, when we pass in node root, pointer to a node root, this address is a copy of another pointer. So what we're doing is we're just pointing this copy, right? We're updating this copy to be the new address of node to insert. Okay, and I'll draw that out right now. Okay. So let's say we have our memory here. Okay. So now going back to our drawing. Okay, so we have, let's say, address 101. And again, like the sizes don't really matter. So just know that they're different numbers. So I'm oversimplifying. Of course, integers are going to be 4 bytes. So it should have been like 100, 204, 104 to 108, and so on. But just want to give you like a kind of like a how the topology works, I guess. Okay. So let's say that we had declared a node root, okay, to be some address. So in this case, in our main function, wherever this node root comes, we'll say root is first, and this will be a node, pointer to be null. We'll first initialize it to null. Then we also create an integer called value, which we can just say, for example, is 20 in this case, going back to our first example. So we have these two things, and what we're going to do is we're going to call insert. Okay, so insert, and then we'll just have our parameters here. So insert is actually going to start at this memory location here, 104. And let's just give it like 3 addresses. I don't know how many it needs. We'll see. Now when you call insert, you're going to create 2 copies. Okay? 2 copies. Pointer to some node called root. Okay? Come on. Why? Okay. Pointer to some node called root. Hello? Huh. That's odd. Okay. Jank. Okay. So root is here. Okay. And that's going to be initially null because that's a copy. And then what we're going to do is create another copy of value because that's the function call, and it'll be 20. Okay? So that's the state of our call right now, the state of our function. Next, what this code is going to do is it creates a pointer node to insert. Okay? Pointer node to insert. So then we say NTI node to insert. And that's going to be basically a memory address. Well, you know what? Let's actually do this. Let's go to create node, and we'll create. There's another function call. So basically, there's more memory allocated down here, and then we had allocated some memory somewhere in elsewhere, and we return the address, and let's just say it's 108 here. So I don't know why this is giving me a hard time. Okay, come on. Okay. So let's just say this is the real node to insert. So result. Okay. Patience. Okay. Sorry. This is horrible. What's going on? Okay, you know what? Is it because of this button? It's locked or something? Oh, and this shuts it off? Okay, weird. Alright, so this is the result from the other function call. So then when we call create node to insert, basically we get back 108. Because that's a pointer, it just leads back to a memory address. So this is the heap. Okay? What we're going to do is we're going to assign, since root is null, we're going to assign the address of node to insert to root. Okay, in this case, now we're pointing. So this actually becomes 108. Now when we exit this function, what happens? Well, as it turns out, this whole thing ends up getting blown away. Correct? So we've actually never really modified this address root here because that was just a copied value. So what do you think we might need to do here if we want to actually create that address or modify the real address up here? First, let's actually just demonstrate what's going on. Okay, so technically, if we were to just get rid of all this, and let's just say, okay, well, n root is going to be null. Okay, address, and we say insert n root 20. We should expect, before we went through this exercise, that n root should be something, since we had inserted and modified the pointer, correct? So we did gcc main.c, a.out. Oh my gosh, we crashed. Why? Because n root was never really modified. This happened right here. So what should we actually do? Well, we should use double pointers, like before. So then, what ends up happening is that we, instead of passing in just a single pointer, we had to get the address of that. Let's see what happens. Oops. What's going on? Warning. Assignment from incompatible pointer type node to insert. Oh, I forgot the dereference. Dereference. We're dereference. Okay, good. This is double pointer. We had a dereference. So in this case, now it works. Okay, so just to review, going so super slow is worth it, I guess. What we really need is not a single pointer to root. We need a double pointers because we want to actually modify the address of the real root. Remember that C is always copied by value. So even pointers, when you pass on pointers, you're just passing a copy of that address. That's all you're doing. And then you have to use a dereference operator to actually go to that real piece of data. But since we're modifying pointers and not really modifying values, what we have to do is actually pass in a double pointer. So an address that will point, well, an address that when you're dereferenced, you'll get back another address, which then you can actually really use. So what we do then is, well, okay, let's create our node as normal, right? We get back an address, whatever, it's in the heap. Now what we need to do then is, since it's a double pointer, we have to dereference to go to the real address, to go to the real reference. Because right now in the stack, it's just the address to the address. So we dereference, well, we'll get back the address. So is the address right now containing null? Well, if so, then, okay, well, let's repoint that real address to be node to insert. That's all there is. So how does that even look like? Again, I understand that it's not not easy. Okay. Can't draw today. What is going on? Okay, you know what? Let's be a little clean. Sometimes I feel like it's not even worth drawing. I just try to use the circles, but okay, let's refresh. Oh, everything's fixed. Look at that. Web applications. Okay. All I needed to do was refresh the page and everything works. But it's funny because the second I touch the touchpad, like, it just gets weird. Okay, so we'll split that into memory cells again. And now let's take a look at the double pointer scenario, just to clarify. So we have 101, 102, not caring about like the real sizes of things. Okay, and then we'll say this is a heap here, and here's where result is after we create. And then here is going to be the node and root in this case. Okay, initially that is null. And then we also have let's just say int val, int v, it's gonna be 20. So actually let's go back to here and then do that just to make it more obvious. Okay. All right. So function call. Function call will then be now just allocate again at 104. And just go all the way down here. And this part is the insert. Okay. So now what we're taking is a double pointer, okay, called root. Okay. This case, well, it's null right now, but we want to know the address of this pointer. The address of this pointer is 101. Okay. And then now we also have int value, which is easy. That is 20. Okay. And then, so double pointer means not to get the value inside here, which was null anyway. What we want to do is get this value here. So in order to do that, it's a double pointer because this one's a single pointer. A single pointer contains an address. Well, in order for you to get a pointer of a pointer, it has to be a double pointer. A pointer of a pointer. So this is actually still an address. Remember that. This is also an address too. It just happens to be null right now. Okay. So we're passing in the address of this address. The address of this address, which is 101. All right. Continuing forward, well, we create this node to insert variable, and that is actually going to be 108. So node to, this is node to I is 108. Okay. And what we want to do is dereference root. Okay. So dereference this memory address. Boom. Go to here. Dereference that. You'll get a null memory address. Okay. Sure. That's true. So you'll dereference this again. Dereference one more time. Go back to 101. Okay. What's the value in here? We want to assign that to be node to insert. So node to insert, again, remember, is a memory address all the way down here, okay? All the way down here. That's a memory address. So we want to assign that, okay, to be 108. Interesting. I'll just draw it. 108. Okay? So, when our function exits, we can blow this away. Blow that away. And we'll actually still have the correct setting once we've exited insert. So, when we dereference en route, so go to 108, to go to en route 108, dereference that, so go to that value, we'll get down to here, which is the original data that we created up here. We'll just get that value. So that's why the double pointer works. Just drawing it this way kind of helps a little bit. So, yeah, that's one case. We've solved the empty tree case. Yay. All right. Well, what's the next case? The next case is a leaf node. Okay, so what is a leaf node? Well, it's any node where left and right are null, but the node itself is not null. Now, at this point, when root, after we're done with checking if root equals null, all the other conditions are going to assume that that root is non-null at this point. So what we need to do is we just need to do this. Dereference that, get that value. If the left is null, and dereference root again to get to that singular structure, right is null, what should we do? We just basically figure out which child to insert to. So in this case, we'll just say if, okay, the node to insert dot value is going to be less than root value. Oops. Dereference root first. Get that value. It should go on the left side of the tree. So then it becomes the left child. Okay. Node to insert becomes the left child of root in this case. Else, well, the right child. Okay, so node to insert becomes the right child root. And keep in mind at this point, when we come here, if left and right of root are null, means that it's a leaf. So we have to figure out which side to inject this node to insert to in root. So in this picture, it just means this. I'm going to use my mouse now. Okay, in this picture, this one is root. Okay, actually we dereference it. That's the value. Because remember, it's a double pointer. So this is null at this point, and this is null at this point. Don't even know what I'm writing now. I'm just saying n. N. So what you want to do is you want to figure out which side to actually insert this node, either here or here. One of those. Which one? Okay? And that is done by checking the value of your node to insert against this value here, the root. If the value of your node to insert is less than the value of root, then it goes to the left side. Otherwise, it'll go to the right side. And that is what we have done here. Cool. Well, what's the third case? The third case is whether or not root has has what do you say? How should I say this? A child, but not both, right? So, uh, okay, so else if root left is null or root right is null. That means either has child. Okay? So what do we do here? Well, we can check whether or not the node to insert could be, in this case, greater than the root, where it becomes greater than or equal to root, where it becomes a right child, or less than the root, where it becomes a left child. But then we also run into problems that, okay, what if it is, let's say, less than the root, the node to insert is less than the root, but the root already has a left child. It's just that it doesn't have a right child. We had to dig through. The other cases, if they both are existing, so not this third case, but the fourth case where root has two children. Okay, so this is where it gets a little complicated. We had kind of treated one child and two children as independent cases before, but now when you think about it, well, it now becomes kind of like one case if they have children in general. Also, how do we actually keep digging in to the tree when we insert? So let's say there's children, we got to go down. I mean, that's pretty complicated. We have to have a temporary variable to try and hold, and then as we iterate down the tree, we'll eventually constantly do all of these checks. So actually, we may have to rewrite this insert. Right now, we're writing it in a way where it works if we somehow find have a tree that's not initialized where it is null, and it works when basically there's only one node. But this doesn't really work when you run into the case where, for example, you have at least one child. So let's actually then kind of do this a different way. Let's actually recursively insert in this case. And I'm going to type it first, and then let's discuss. So we're going to have to refactor our function a little bit. We're going to have another function called insert, where we do take a root, and we do have a value, same as before. But we're going to call this one insert helper. And what we're going to do is, instead of passing in the int value, we're just going to pass in the node to insert. Okay, this one here gets created down here, and we're going to be using this one to call. This one kind of serves as like a private helper that we're going to be using. Okay, and now what we want to do is we're just going to call insert helper with root and also the address to node to insert. Okay. Well, actually, I think we can just do single pointer. Yeah, we just do single pointer. Yeah, I think that works. Okay. So, first and foremost, let's actually bring this logic root equals null to here, so we can immediately just solve that problem and not call this insert helper if the tree is empty. So we'll say root is now node to insert. Okay. And then once we solve that, we just return. So we can just get rid of this code here. And that simplifies things a little bit. So actually, let's just test to see if we broke anything, right? So technically, this stayed the same. Okay, we should return immediately when our tree is empty. So we should still be getting 20 back. Great, so we're still good. So this is going to be our main function that will handle things. This one here will be our helper. Okay, so far so good. All right, so let's kind of solve this a little bit. All right, so recursive function always needs to have a base case. Otherwise, we'll constantly just dig down infinitely and cause a Stack Overflow. So I'm going to just ignore this and just rewrite it where, what is our base case? Well, our base case is if we can finally insert something to the tree. In this case, we want to insert something when, well, let's say first of all, we have a leaf node. So let's make it easier and do something like this. Node, per node is going to be dereference root. Okay? So now we can just treat cur node as a normal, as if we passed in a single pointer. So if cur node left is null and cur node right is null, okay? Then what we want to do is this same logic. So if node to insert value is less than cur node value, and we'll make this better as we go along. We want cur node left, okay, to be node to insert. Else, we want cur nodes right to be the node to insert. Okay, and we just return. That's one case. So we can just clean this up a little bit. Don't need that anymore. And now we're in a case where, well, what if there's one child? So let's rewrite this bottom one here. If cur node left, okay, is null, or actually this actually doesn't matter at this point. Okay, so we know that at this point there's only going to be either you have a child or you don't. Okay, so we'll say this: if cur node left is null and cur node's value, okay, basically if the node to insert's value is less than cur node's value, it becomes pretty easy. It just means cur node's left is going to be node to insert. Okay, and then we can return. Otherwise, if cur node's right is null and node to insert value is greater than or equal to cur node value, what can we do? Well, cur node's right is going to be node to insert. Return. Okay, so this is when you have one child or the other, or it could just be that you have, you're at you have one child. Wait, you could have a situation where you have two children or one child. Basically, you're just going to check for null, and if one of them is null and this condition fits, that's great. You can just insert it directly as long as these things are true. Okay, but you're going to run into situations where, well, okay, this is not going to be true, and this is not going to be true because left and right will exist, or in this case, we have a left, but the value is less, and so this is never true. This isn't caused to be true. You want to kind of just drive and dig down. So you want to call insert helper, okay? at the appropriate spot. So in this case, we want to either go to the left side or the right side of the tree. Okay, so if node to insert value is less than current node's value, at this point, we know that there is something on the left side. So what we want to do is we insert helper, and we're going to change our route. We're going to change our route to be, in this case, left. We want to go left because we know node to insert is going to be less than current node. So we want to go left to that next node and compare node to insert with basically that new node on the left side of the tree. And we want to pass down node to insert here too. Otherwise, we know we need to go right. The reason why I'm doing this ampersand here is to get the address to turn this back into a double pointer. So basically something like this, if you think about it. I'm turning it back into a double pointer. So, oops. Like this. There we go. Okay. At this point, then, we're going to drive either left or right, and then insert our node at the part where we eventually run into a situation where we either have no children, or we have one child, but we need to know whether or not it's left or right child. Otherwise, we just keep going in whatever direction, left or right. Oops. I hope this works. I'm just mentally like doing it. I'd say let's just test it and then we'll walk through the code because I don't want to just walk through only to find out that I'm wrong. So what we want to do is let's do this. Insert starting at the root. Let's insert 10. And then let's insert 30. And then let's do this. Let's do in order at end root. Let's see what happens. I really need to print that new line. Okay. Here. Okay, there. So we got 10, 20, 30. That is in sorted order, and that's not the same order we inserted the tree or the nodes to the tree. Okay, so actually I'm going to keep testing. I'm going to insert more data into the tree. I don't need this. I could just do it this way. Okay, so I'm going to insert, let's say 15. I'm going to insert, let's say 35, insert, 5, insert, 25. Okay. So if I were to draw this, what this tree is going to look like, if my pen cooperates, okay, what this tree is going to look like is we first insert 20, and then we insert 10, and then after that we insert 30, then we insert 15, so left, right, then after that we insert 35, so right, right, then we insert 5, starting from here again, that's always be our root, left, left, then we'll insert 25, right, left, and let's actually insert one more. Let's do insert 45. No, let's do 27. 28. Fat finger. 28. Let's do 28. So we'll insert 28. So we go right, left, right. So that's what our tree looks like. Okay, so let's actually do an in-order traversal just to see if we get expected 5, 10, 15, 20, 25, 28, 30, and then 35. Hopefully that's what we get. So let's do it. GCC. Okay. 5, 10, 15, 20, 25, 28, 30, 35. So we've inserted to the tree correctly. That's the most important thing. So this algorithm for our test case right now works. So we have an insert helper and then an insert here. Okay, so let's do this test case again, but this time let's step through our code. Okay. In order to facilitate keeping track correctly, I'm going to make sure that, how should I do this? This is going to be long code. Yeah, let's actually break this code down first. Because I want to make sure that we can see this. We can see everything. In like a thinner view, I guess. Okay. Then, like column, you know? Is that enough indentations? Yeah. And then maybe this is enough. Yeah. And then, okay, so let's see. Let's see if that's gonna fit. Okay, so we can kind of shrink this down a little bit to that point. And will everything fit? It looks like it. That's great. Cool. Cool. Okay, and it's still readable. All right, cool. All right, well, let's see. Can I zoom out here just a tad? So then we have some more space. I'll just draw bigger. Anyway, let's start an insert. Okay, let's start an insert. So let's draw our stack. So let's do stack here so we know what's going on. Okay, so here's our stack. And here's gonna be our tree visually. Okay. And then this is always going to be pointing right now to null at this point. Okay, because end root is null. All right. First things first. Okay, we're going to call insert with our end root with the value 20. Okay, and let's just assume that create node always creates us the right thing. Okay, so we're going to pass in end root is null in this case, and then v is going to be 20. Okay, so when we go to insert, we actually have node to insert, which is going to be basically a node that has 20 as the value. So we can just say, well, in this case, we'll create a node to insert. That is 20. Okay. And then after that, we're on line 92 here. Okay. Well, that root is null. So we actually create node to insert to be the new root. I have no idea why my pen is weird. Okay, so this is now the new node. So root is now node to insert. So we can just say, well, now it's 20. Okay. So we return. At that point, n root is now 20, but then we also pop this off the stack. So let's erase that. Okay, let's erase all this. So now we're good. This is now n root. All right, next call is going to insert n root with 10. So n root is 20, and I'll just make it like this to make it look like a node, and then value is going to be 10. Still haven't figured out a good way to draw these things. We'll get there as we do more of these. So we call it insert, and well, root is now something. It's the 20. Okay, so we don't go to that null condition to set node to insert to be root. Instead, we're going to go to insert helper. So insert helper. So we go insert helper, and then now we pass in that root. Okay, sure. We find that, okay, the left side is null, and also the right side is null, given that it's just 20 here. Okay, now we need to check to see if the value of 10 that we're creating, so at this point, node to insert, is 10. Is that less than whatever the root's value? Well, yes, it is. So basically, we just assign the left side to be the node to insert, which is 10 right there. Okay. And then we return line 66. So when we return, we just pop this off. Okay. Okay. Next line of code is going to be 30. Okay. So again, we call it insert with 20 as a root, 30 as a value. We create that node to insert with 30. So we just type that or write that here, node to insert, just to remind ourselves. Okay, it's 30. This doesn't apply, so we go to insert helper with root as 20. Okay, with 30 as a node to insert. Going to the insert helper here, well, we find that we're at 20 right now. This is where we're at right now. Current node left is not null. So, okay, so already we know that this condition doesn't apply anymore because it only applies if the current node left is null, meaning the n root, which is currently 20, is null, and the right is also null. But right now we have left being a node of 10, and the right is null. So let's go down here. Well, current node is already not null, so we skip that here. Current node right is null, and node inserts value 30 happens to be greater than the root's or the current node's value, which is the root, is 20. So then we insert this node to insert to the right side of our current node, which is actually 20. I'm going to ignore this thing now. I didn't update it because it's too confusing for now. I need to figure out how to draw this better. Okay. Let's actually be disciplined on the next one. Okay, so now we return. Okay, so that's good. So far, so good. Now, this is where it gets interesting. 15. Now, this is where I need to be much more careful keeping track of things. So, I'm going to try my best to stay disciplined. N root is going to be 20. We start at 20. Okay. And then V, actually, let's do this. Let's do how we used to do it. This is like 20 and then 15. Let's just do that. Make it easier. So I'll call insert. with 20 and 15. So going back up here, we create a new node with 15 as a value. Okay, well, our root here is 20. So then we don't execute this code because it's not null. So then we call insert helper. Okay, insert helper. Let's just be more disciplined. With 20 and the node to insert, which is 15. Okay. And going into here. Okay. Well, right now we're at 20. Okay. Cur node is left is not null. So we don't check this one because we short circuit. And we already know that this is not null, so we're gonna go here. We know that right is not null because we have 30, so we're left with this. Okay, so what we're going to do is we're going to check, is the value 15, which is node to insert's value, less than the current node's value? Well, yes, it is. So what we want to do is we actually want to call insert helper. With the left side of the node, which is going to be 10, passing in still the node to insert. So then we're going to call this function with actually changing the root parameter argument here to be now the left side, which is 10. So let's call insert helper again, going back up. Well, now we check. We're at 10 now. Current node is technically 10. Is the left side null and the right side null? Oh, yeah, it is. So let's check. Okay, well, is the node to insert value, which is 15, less than the current node's value, which is 10? No, it's not. So we go to the else. Current node's right happens to be the node to insert. So we go insert the right side. Great. Then we return. So when we return, again, we just pop off the stack, like so. And then we're back at this function call here, going to the next line because we don't need the else condition. Turns out we're done here too. And then now we're back here with where insert helper was with 2015. Turns out we're done there too. And there, we're clean. So we've inserted 15 in. So at this point, I think you guys can figure out like how to do this here. It's just that the hard part is when you're keeping track of recursive calls, it's like I couldn't even manage this too. So because I was trying to do it clean, but I think I'm out of practice when it comes to drawing that. So let's just do one more, just for the sake of practice. Let's do 35. Let's insert 35. So inserting 35, we're gonna call insert here. So let's draw our stack. So this is how we should really draw our stack for now. Okay. Call insert with 20 as our root, then 35. So when we get to here, what ends up happening is that, okay, we create that node to insert, which is 35, pretend it's already there magically. Root is not null, so that's fine. So now we call insert helper with the root, okay? So insert helper with 20 as a root, and then node to insert is 35. So we're here, now we're gonna go up to insert helper, and well, let's see. Right now the current node is 20, okay? We check the left side. Is it null? Oh, it's not null. It has 10. So this condition doesn't hold anymore because short circuiting. How about this side? Well, or this if condition. Current left is not null because that's 10 already where we're at 20. Okay, so we move on. How about current node right? Is that null? Current node right, is that null? No, it's not. It has 30. Okay, we move on. Okay, great. Now we're at this point here. Okay, is 35 less than 20, basically. Is no we want to insert 35 less than the value of the current node. No, it's not. So we go to the else. So now basically what we want to do is call insert helper with the right child of the current node. So that happens to be 30. So we'll do insert helper with 30 and 35. Okay. So we'll call insert helper again. We'll go back up here. Okay, well, 30 is the current node. Left is null, and right is also null. So we're in here now. Node to insert is 35. Is it less than the current node 30? No, it's not. So we go to the else. Well, then we just simply assign node to insert as the right child of the current node, which is 30. And then next line, we return. So we just get out of here. Uh-oh. All right. We'll just use the mouse now. Okay. So we return. So now we're back at this call where we had actually passed in the current node right with node to insert. So that's done because we're exiting the function. Okay. Now we're back out here where we had called insert helper initially. We're done with that too. Okay, and then we're done with that too. So then we're clean again. So then we just do this repeatedly with 5, 25, 28. We just keep digging in. The trick again is to keep track of your recursive calls. So yeah, that's our insert. Yeah. It's a little mind bending, but we got there. BST insert. Okay, the next one we're gonna discuss next time is going to be, let's see, deletion. Yeah, deletion. We'll do deletion, and that one is super complicated. So, another trip for drawing and thinking and stuff. All right, talk to you soon.